Hello everyone, my name is Deepak Kumar and today my team and I are here to demonstrate our project ThreadLab, a real-time multi-threaded application simulator. Through this simulator, we aim to visualize and analyze how multi-threaded environment operate in real time.
Hello everyone, myself I am Sai Krishna, student of BTech section K424. I am at Lovely Professional University, Pagwara. Today I am presenting my OS project titled ThreadLab Real-Time Multi-Threaded Application Simulator.
Hello everyone, my name is Madhav Yani. I am student of BTech section 424 IM at Lovely Professional University, Fagwara. Today we are going to present our OS project for the course CSC 316 under the guidance of my respective faculty, Isha ma'am.
So let me first explain the problem statement assigned to me. The problem statement is to develop a simulator to demonstrate multi-threading modules, many-to-one, one-to-many, and many-to-many along with thread synchronization using semaphores and monitors. The simulator should visualize thread states and interaction, providing insights into thread management and CPU scheduling in multi-threaded environments. In simple words, operating system concepts like threading, synchronization, and scheduling are very theoretical. Students read about them in books, but cannot actually see what happens when threads compete for CPU time or when a deadlock occurs. So my objective was to build an interactive simulator where you can watch threads running, blocking, waiting, and completing in real time with live animation. The application has four main modules: thread modeling, synchronization, CPU scheduling, and deadlock detection and resolution. So now let me explain the methodology and tools I used to build this. So we have built this ThreadLab using three core technologies: JavaScript, HTML, and CSS with absolute zero external frameworks. This was a deliberate choice to keep the code readable, portable, and easy to run anywhere. The application runs on Electron desktop app, which means it works on Windows, Mac, and Linux, and also a static web app that can be deployed in Vercel or any web host. The architecture is divided into three modules. First, the simulation engine, a pure JavaScript module with no UI dependency and models all thread behavior using a tick-based clock. Second, the GUI module, which handles all user controls and rendering. And third, the visualization module, which generates live SVG diagrams, show thread states, mapping, Gantt charts, and resource allocation graph. The project is controlled on GitHub. It's a repository with almost 11 commits are made into this. So let me now show you with animation. So this is the thread modules tab. Here I can choose between many-to-n, one-to-one, and many-to-one. So I selected many-to-many. This is an M2N model where multiple user threads are multiplexed over a simple number of kernel threads. We can add threads from here and we can run. It will show our output in this manner. You can see the activity log has been monitored here, how user thread will work, their percentage of process done, one-to-one process, and obviously many-to-one. We can add threads along with the process. When I click run, you can see the threads, they are live. The green chip shows threads that are running, amber chip shows threads that are waiting for IO, blue chips are ready, and the gray ones are done. Notice how the kernel threads K1, K2, and K3 are being shared among the users threads U1 through U6. This is exactly many-to-many model. This is the exact many-to-many model. If one user thread blocks, the kernel thread picks up the next ready thread automatically. The mapping diagram at the bottom shows real-time connection between user threads and kernel threads. So now I will show you the synchronization module. I selected semaphore with an initial value of 2 to 5 threads. 2 to 5. Now see here, the semaphore counter starts at 2. Thread T1 and T2 immediately acquire the semaphore and enter the critical section. You can see the counter drop to 0. Thread T3, T4 and T5 are now blocked, shown in red, because the semaphore is at 0. They cannot enter until a thread signals and releases. When T1 exits the critical section, it calls signal. The counter goes back to 1 and T3 immediately unblocks and enters. This is exactly the wait and signal mechanism of counting semaphore, demonstrated live. So next, the CPU scheduler. I've already selected round robin with time quantum number of 3. When we run, you can see that the Gantt chart is building in real time. The Gantt chart, each row represents a process, P1 through P4. The colored bars show which process is running at each time tick. The ready queue on the left shows which process are waiting. CPU core card shows the currently running process with its completion percentage. At the top, you can see live statistics, average waiting time, and CPU utilization. I'll run it again. You can see. Now let me switch to the shortest job first and run it again. Shortest job first. Notice how the order of execution changes. P3, which has a burst time only of 3 ticks, now runs first, reducing the average waiting time compared to round robin. This is how ThreadLab lets you visually compare different scheduling algorithms side by side. So let me now summarize the results and key observations from this project. First, comparing threading models. The many-to-one model showed sequential execution with complete blocking on I/O. The one-to-one model showed true parallelism. Blocking one thread did not affect others. The many-to-many model balanced both efficiency and parallelism. Second, for CPU scheduling, in my test with 4 processes, burst times 8536, shortest job first achieved the lowest average waiting time. Round robin was the fairest but had more context switches. FCFS was simplest but suffered from convoy effect. The application runs smoothly in both Electron desktop mode and in browser. It is deployed and accessible in the GitHub repository, has 11 commits across 4 branches showing full development process. To conclude, ThreadLab successfully demonstrates all the concepts required by the problem statement, threading models, synchronization primitives, CPU scheduling algorithms, all through real-time interactive visualization. This project helped me and my teammates deeply understand how an operating system manages threads, handles synchronization, makes scheduling decisions, and recovers from deadlock situations. The complete source code, project report, and documentation are available on GitHub of me, my teammates. Thank you for watching. I am Madhav Yani along with my teammates. Thank you, Isha ma'am, for your guidance throughout this project.